Buongiorno, bonjour, hola. So this is the episode where I answer your question. Can you use Python to find your keys? That is the question of the hour. That is the question that we're going to answer today. Well, I'm going to cut straight to the point or the answer. And the answer is, well, perhaps. But for the purpose of this episode, I'm going to show you how you can actually use Python very easily, I might add, to do a face detection. And it's pretty simple to do. Now, there can be a lot of advanced math involved, actually there is a lot of advanced math involved, but I'm going to show you the secret how you can avoid the math, because we all love avoiding math, right? No one likes to be involved in unnecessary math. So I'm going to show you the secret using Python right here on this channel. So go ahead and click on the like button, subscribe if you have not subscribed already, because you don't want to miss out on future awesome videos just like this. And this is Carlos Speaks Wall Street. And today we're going to do object detection using Python. Let's begin.
With options, your entire strategy is based on what you think. I'm going to give you the fixed protocol. Options Greeks.
Go ahead and click on that subscribe button and welcome aboard. Also, click on the bell.
All right, so let's get right into the news. Not quite. So basically, the secret to being able to access the power of machine learning is basically you can use Python as sort of a conduit or gateway into the magical world of machine learning, utilizing a library that plugs you directly into an API for code that's actually written in C++. But you don't need to mess with the C++. You don't need to mess with that. All you do is you act as the, shall we say, puppet master, the one who pulls the strings. Don't really need to get too much under the hood and looking at the math and techniques and algorithms behind it. However, you should have a basic understanding of the concepts involved. And I'm going to give you a glimpse into that. We're also going to do a demonstration today to show you the power of this facial detection. And I'm going to show you how easy it is on this episode. So let's go ahead and get right into it. So here we go. So I'm gonna jump right in, and we're gonna do a quick demo right now to show you how this wonderful technology works. So I'm going to do a image scan on my medium image. So basically, I'm going to run a very small Python file that has the basic instructions required to basically utilize a machine learning library to be able to scan an image. The image in question is a photo called mediumgroup.jpg or JPEG. Yeah, same thing. And I'm going to go ahead and run it, and you're going to see it's going to scan the photo and try to identify faces. So without further ado, and watch it crash and embarrass myself. You guys can see that. Yes. Okay. So there we go. So here's the photo. Never mind my theme errors. I got to clean up my environment. But what matters is that we have success. Kapla for the Trekkies. Anyway, so in this image, we have several people standing in a group, and our little very basic Python script was able to scan this image and actually pick out all of these faces and draw a box around the faces as well. Now, it did not pick up every single face. There is a guy in the back. If you look back here, you can see His face is partially obscured, so did not recognize that. Now there's some parameters that we can change to pick him up as well, and I'll show you that in a little bit. Also, this guy as well, a lot of his face is obscured, so did not pick him up either. So a few people didn't get picked up, but this is generally the concept. Scan this image, recognize potential faces, confirm that they are faces within a certain threshold of confidence. So there's a concept, one of the many concepts in terms of your confidence level. So the application tries to determine or tries to classify an object. Is this a face? And it's kind of something, for those of you fix protocol folks, it's sort of, in a way, very simplistically speaking, like a heartbeat, where it's, you know, are you there? Are you there? Are you there? Are you there? This constant asking the same question over and over again, just to sort of maintain the connection status. So in a similar vein, there's this loop that we run where, and again, there's different strategies, different types of algorithms, but this is a common pattern that you'll see where the program will constantly ask, is this a face? Is this a face? Is this a face? Is this a face? And based on the answers to that question, and the answers will generally be in some form of confidence level. So what is the probability? Probabilities are huge with image detection. What is the probability that this is a face? Right? And then based on that answer, and if it's above a certain threshold, then it could get classified as a face or not a face. So I'm pretty sure that the guy in the back, that question was asked and probably got some good hits in terms of might be a face, but the confidence level wasn't high enough, so it rejected it as a potential face. But we can, of course, we can tweak that. So let's jump into the code. Let's jump right into the code. So we are going to take a look at the imagescan.py. I'm going to show you how basic it is. Just run you through what is happening. What is happening? Before we do that, let me just make sure do a quick sound check, make sure the sound is good. All right, the sound is good. Bellissimo. Dobre utro. So here we go. So this is the file. So this right here is everything that is required to do well from a user perspective anyway. I am, again, consider this program to be the puppet master, right? So there is more required than just this script, but this is where we're pulling all of the strings that make this happen. So everything from a user perspective, and when I say user, I mean in terms of, let's say, whatever you consider yourself to be a developer. So you want to build something so that you can detect a face. So from the perspective of the creator, the designer of this product that's going to do that, this is everything that you need essentially to be tinkering around with, configuring. This is it, right? So I'm going to show you some of the dependencies that are behind this, but essentially this is your playground. This is where you're going to work. So this is this is everything. This is the bottom line. That's the final line of our code. So if we go up to the top, we have the shebang, of course, and we do two imports. We're importing CV2, that is from the OpenCV project. CV referring to Charlie Victor. Phonetic alphabet. No, it refers to computer vision. So computer vision is essentially the way that, or methods for a computer to be able to see. So for example, if you have software that's going to process an image, obviously a computer does not have eyes. A computer does not have the capacity to see things the way we see things. Everything is just data, it's digital. So computer vision techniques, algorithms, methods, strategies allow the computer to be able to see things in order to do things with images, video, pictures or video, right? So this CV2 library possesses or contains a lot of information that will allow your computer to be able to see things. In addition to that, it enables us to be able to do our processing to be able to detect the faces. So that's the first thing. Sys is standard library that allows us essentially access to the local environment. So let's say you wanted to be able to run a shell command or something like that. Sys will allow you to do that. So that's it. So we're only importing from 2 different libraries, CV2, Computer Vision 2, version 2, and Sys. That's it. Real simple. This is a simple comment here, and then we have an argument statement here. So all this is doing here is this is telling the program where the actual image is that we're going to use, right? Because the way this works is it's going to process an image and try to detect faces in there. So where is the image? What is the image that we're processing? Well, the image is going to be argument 1. So you see we're utilizing sys, which we imported here, and then we're doing a dot arg or argv. I call it arg. You can call it whatever you like, but it's looking for an argument. The specific argument is the first argument. So if you look at what we typed in to run this before, you will see this is our argument 1. We ran the script and we gave it a single argument, and that single argument from the context of this program is image path. So basically that's a variable. So this variable that is going to contain this image that we're using. So that's what we're going to scan. So all we're doing here, this is kind of shortcuts. So we're basically creating variables for the convenience. So we don't have to, like, for example, we don't have to keep typing this in over and over again. So what this is this is a cascade file. It's a har cascade file. It's a har. Okay, that's a horrible joke. Anyway, so this is a cascade file. Cascade file is, and once again, there's a lot of different methods that you can utilize to use to detect images. And in this case, detecting faces is what we're specifically trying to do. A cascade is or a har cascade is one of those methods that you can utilize to detect a face. Again, different algorithms. So there's various algorithms that you can utilize to detect images, objects, faces. We are using a har cascade. So the reason for this file, and we can take a quick look at this file. The reason for this file is you can't just simply utilize some magical algorithm that's going to just magically, that's a face, that's a face. So with machine learning, and specifically with object detection, there's several phases to how things work. And at the end, you have classification. So you have a concept of classifiers. So for example, you could have a facial classifier, you could have a car classifier, a house classifier. So what that means is, what are the various categories of objects that you are capable of detecting? So whenever you're processing an image, whenever you're scanning an image, it will be in the context of those categories. So in this particular case, what we're using is a har cascade file, which has, as you can see here in part of the name, frontal face. That is the category of what this file looks for. So again, in the workflow of object detection, at the end, we have classification. In the beginning, we have a training process or a data. You need to have your data. So for example, again, like the algorithm can't just magically detect a face, right? So you need to train it. You need to give it information in terms of what an actual face is. So imagine, I think a simple example would be, imagine you are, where I'm seeing this, I guess in elementary school, you might, when you're learning words and things like that. So imagine if, you show like an index card or something and you show like this. What's this? This is a cup. Okay. What's this? This is a phone. Okay. And then it's kind of like, okay, is this a phone? No, that's not a phone. That kind of thing. So you have to somehow produce training data. This is the data that represents information regarding, in this case, what a face looks like and what a face doesn't look like. So when the image processing is being done, it's going to utilize this facial data as reference to determine what a face looks like. So I guess another analogy as well is, imagine if you are working for the Secret Service and you're going to an event where there might be some terrorists at the event. And before you go there, you are shown a series of photos of a few suspects, different, you see them, casual settings, surveillance photo, whatever it is, different kinds of photos, them dressed in different ways. And so that's your data, right? And then the training is you watching these photos, and you want to see not just one photo, because they may look differently in different settings, right? They're in a professional setting versus casual setting. So you have a bunch of photos that you look at and you train your brain on what these suspects look like. And then when you're in the party or the event, you do your scanning of the faces and you're looking for a match. And you may see someone that it's triggering in your brain that this guy looks familiar. You may need to refer back to your pictures, and this might be this guy. So you're not sure, but you have a confidence level. And based on how high that confidence level is, you might take action and be like, I think that's him. Let's go stop that guy. Or no, I don't think this is him. So that is how a human would deal with that scenario. But the way computers deal with it is not that much unlike the way we would. So once again, you have to have the data in terms of what you're looking for. So what do faces look like? So within this file, we have that. So this file, we're just referring to it as a variable. And let's continue. So here we have another variable that we're using called face cascade. Face cascade is, again, this is just a variable that we're creating. We're pulling from the CV2 library that we imported up here. So we import CV2 here, and then we're calling. So in Python, that's a syntax. When I like to say, I don't know if anyone else does it, but I say you dot whatever. So we're dot cascade classifier. So we're basically pulling cascade classifier from CV2. Now we can actually see inside of this library by pulling up the Python interpreter, and we can see what all these things are. So for example, if I were to search for cascade, we could see that it does not come up. Let me see what I'm doing here. Cascade. There we go. So there's cascade classifier. So this is in the actual library itself. Now I don't need to mess with this. This is just for reference. So you can get the correct spelling and things like that and know what the syntax is. So see, it says cascade classifier, and then it has these arguments in here. Now, so that's what I'm referring to when I say CV2 cascade classifier. I'm trying to pull cascade classifier from the CV2 library, and I'm giving it this argument, which is cascade path, which we set here. And all that is the location of that file, the XML file that has the data that we're going to use to recognize a face. So pretty simple. So continuing along, I don't want to spend too much time on this. I just want to give you guys a quick overview. But here we have a scan image. So we're doing, again, more variables. So we're setting a variable image, variable gray. We're pulling IamRead from CV2 and CV2 color from CV2. So we are basically pulling these two right here from the CV2 library, and these are the arguments we're sending. So we're giving the IamRead, which basically, as the name suggests, this is basically where you want to actually read the image. To actually read the image, you're going to do an IamRead. What are you going to IamRead? You're going to IamRead image path. What's image path? Image path is simply what we set up here. We declared image path to be argument number 1, right? So when we run the script, we give it an argument being the name of the image. When I say image, that's the photo we want to scan, right? So basically, whenever we want to actually scan the photo, we're going to do an IM read of the photo, which is what that refers to. Here we're doing some pre-processing. So again, a lot of strategies in terms of how you do your face detection, how you do your analysis. And one of the primary concerns is efficiency. You want to think about how efficient your program is in terms of utilizing system resources, memory, CPU, because if you don't, your software can take a very long time. So think about right now we have 2K and 4K images, video and photos, and think about you're going to scan, let's say you're looking at a 4K video. The 4K video is presented at a frame rate of 30 frames per second. That means for every second of video, that's 30 frames. Each frame needs to be scanned to see if you can recognize whether there's a face or not. So imagine a 4K image, how many pixels there is, and you're going to be scanning, looking at all these pixels, and then you're going to be assessing, is this a face, is this not a face, is this a face, is not a face, is this a face, not a face, and then you got to go to the next frame. And now you've only done one frame of 30. And that's of 1 second of video. So you can imagine that could take a very long time. And if you're not smart about how you do things, then it could take forever to process things, right? Especially video. So one particular strategy being utilized here is I'm converting the color image to grayscale. So from CV2, I am dotting the color underscore BGR to gray. So that's basically converting to gray. And if we scroll down here, and we're almost done. This is pretty simple, pretty basic. And you guys that are just joining in right now, go ahead and click on the like button. Really appreciate it. And let's scroll down. And we see here, so these are the parameters that are going to govern the face detection. Like you saw how we missed some faces? Well, that's because we need to tweak some of these factors. But basically what we're doing here is we are dotting the detect multiscale from face cascade, and we are giving it these arguments here. So scale factor equals 1.1, min neighbors equals 5, min size equals 15, 15, and flags equals cv2.cascade. So these are pretty simple. So without getting into too many details, unnecessary details for the purpose of this video. So scale factor is basically there is a method that is being utilized where we are processing the image in several phases, like the way that the computer is able to process the image, and it actually takes the image and it'll shrink it and blur it and do several operations with the image in order to assist in the efficient processing of that image. And scale factor is basically let's just call it step size between each phase of the process, or each phase of the iterations that is going to go through to get to the processing of the image. Because one of the methods that are utilized to do image detection is something called a sliding window, where literally the way that the computer will process an image is it'll actually, probably be better like this, it'll actually analyze the image. Like, imagine it's looking at it from the context of a box. Imagine a virtual box. So it'll process this, process that, process that, process that, process that, process that, process that, and it just keeps scanning across the image from left to right, for example. And it'll do that at a certain resolution, and then it'll downscale the image and do it again, and then it'll downscale the image and do it again, and it'll also apply a Gaussian blur, for example, to the image as well to eliminate unnecessary details. So this has to do with that operation. Now, without you getting too complicated and too, because the whole point is I wanted to show you how simple this process is. You can just take that basic understanding of what it does, or the relevance, and tweak it. Basically change the values and see what it does to the detection. And then you figure out from yourself, from just from looking at it, you try and figure out how it affects the results. And min neighbors, and I'll do, if you guys want, if we get 40 likes on this video, I'll do an in-depth video on these parameters and how they work, and I'll show you more details, but this is just a general overview. Now, min neighbors, just consider that to be a quality option. So by increasing this number, you're going to increase the quality. When we say quality, you know, what will it take for you to say, yeah, that's a face versus nah, that's not a face? If we increase this value, then what we're going to do is we're going to make it be very, very picky in terms of that really has a lot of characteristics of a face, but nah, it's not good enough. I don't think that's a face. Now you lower the number and it's more casual. It's kind of like, ah, yeah, that's a face, that's a face, that's a face. You know, actually in the photo, if you look, if you notice, it actually detected a face on the woman's shirt. There was no face there, obviously, but the min neighbor's value was too low. Min size is just showing you how small of a size of a face it can detect. I don't have a max size, so it'll detect a face of any size larger than 1515. But anything smaller than that would not be detected. So imagine if you had a picture of someone's face on your pocket. Based on these values, it would not pick it up. No matter how clear that face is, no matter how many, you know, how much of a good features of a face, you know, irrelevant. Doesn't matter about the photo. It's below the threshold of what this is going to look for in terms of a face, so will not detect it. Now, in the end, and we're practically done at this point. Only thing else is we're doing a we're printing out. So that's what you saw when you see the photo, when you see the boxes. So it'll print out to the screen that it found a certain amount of faces. This value here will be replaced with the amount of faces that it's found, of course. And additionally, and see, it's doing a dot format len to faces. Now remember, faces is what we declared here with all these settings. Now I am about to sneeze, possibly. So
with options, your entire strategy is based on what you. I'm going to give you the fixed protocol. Options Greeks.
Go ahead and click on that subscribe button and welcome aboard. Also, click on the bell icon. You have to do this because
and we're back. Bonjour. So we are just about done. So basically this just says how many faces that it's found. And then here's the boxes. This is where we're drawing the boxes, the green boxes around the faces. So we're basically doing a for loop, and we're inserting or taking from faces. So we for X, Y, W, and H in faces. And then we have the CV2.rectangle. So we're pulling or dotting rectangle from the CV2 library. And then I just put a window label on the window that shows the faces. And we're showing, what I did is I put this, I used same thing here. So I'm displaying the number of faces that were found. And then I'm just saying, so I'm saying number of faces found, faces. So 50 faces, yay! Basically is what I'm saying there. And then that is pretty much it. This is a delay. This CV2.wait key, right now it's set to 0, so it does not, that's basically no delay, but you could set a delay there as well. So that's pretty much it. So what I'm going to do here is just show you a quick example of, before we wrap up this live stream. And congratulations, you actually stayed this long for this video, so this must be of great interest to you. And you are one of the very few. You're one of the top 1%, because most people probably disappeared within the first minute. Anyway, so let's jump in here. So what I'm going to do is I'm going to increase the min neighbors to a higher value. So let's be aggressive. I'm feeling motivated. What do you want to call it? So min neighbors from 5 to 55. So let's run this. I'm going to save that. Now let's go ahead and run this again and see what happens. How many faces it detects. So you see there's a huge difference in terms of the amount of faces that are detected in this image, because we set the precision to be so high, or the neighbors parameter to be so high, that a lot of the faces are not picked up. Now you're probably wondering, what is so special about these faces that it detected? Because for example, this woman actually has glasses and not even that stopped it from detecting her face. Here's another woman with glasses, did not detect her face. So it may seem kind of random and kind of all over the place, but that's because you don't understand the math behind this, and neither do I. It is a little bit complex to say the least, but if you really want to master this kind of technology, if you really want to build some powerful, very customized application for your specific purposes, then you're going to want to dive a little bit deeper than what I showed you. Now, I showed you how easy it is to just detect some faces. So if you want to build an application that has the capability to recognize faces, you can do it very, very easily. But if you have something that's a more specialized usage, then you're going to need to understand a little bit more, because simply tweaking these values and seeing different results, it's helpful, but only to a degree, because once again, like I pointed out, why does it not recognize this person, but it recognizes that person? It may not be immediately apparent to you what is so special about these faces. This woman even has her eyes closed, right? And again, to understand that, you need to understand the math behind this, the algorithms behind this. So that was one thing that we changed. Now we can go in and change another value. So we change that to 5. Let's change the min size. Let's see what happens if we change it to 5. That should be interesting. I don't think it's going to detect any faces this time. I don't think there's any faces that'll fall within that, but we're going to find out any moment now. Oh, okay. So these faces are pretty small. So did not really see a big difference. So it's still 65 faces. So it did not affect our face count. So let's dive into here. Let's do min size. I'm actually being ridiculous. This is min size. So all lowering this is going to do is allow us to pick up smaller faces. So what I needed to do was do a max size to limit the bigger faces. So let's see if we can do that right now. So let's do a yank and a put, and let's do a, instead of min size, let's do a max size, if my memory serves me right. And let's do a 15. So no faces larger than 15 will be detected. Let's do this scan again. Okay. So clearly we can see from this that all these faces are larger than that. So we will need to increase that value. So let's be a little bit aggressive with this, and let's try. I mean, knowing the resolution of the image would be very relevant information in terms of the facial sizes, but let's just see what happens. So there we go. So now we know that the size of these faces are somewhere, let's see, 55, so 57 faces. So some faces did not get picked up. So most of the faces that, well, pretty much all of the main ones that didn't get picked up, except for the ones that are partially obscured, are the ones in the front, which makes sense. So I'm going to take a guess, and that I don't want to say literally they might have the biggest heads in this shot, but mathematically speaking, they probably do. When I say mathematically speaking, based on the math and the algorithms that are used to detect faces, these faces are somehow larger. So I don't know if it's the distance between the eyes. That's why I said it's mathematically speaking, because you know, to a human, we probably look at the size of the face as a whole, but this is something that's looking for a certain pattern probably based on primary features like the eyes. So again, distance between the eyes could be a factor as well, or they could actually have the largest heads in the front row. But what we're gonna do now is, and actually, so that means that some of these faces are close to that 55 number that we set, because most of the faces fall within that, but a few of them did not. So that means that some of them are right on that line. So that means we're pretty close to what these the size of the faces are. So let me see if I can get it to the middle of the row. Let's see if we can do that. What's the middle of the row? Average head size. So let's go 45, 45. And let's run that, see what happens. Okay, so that's pretty good. That's actually pretty good. We cut the group in half. So obviously the further away from the camera, the smaller your face, you know, relatively speaking, the smaller your face appears in this photo. So because I set the cap at 44, we're not picking up these larger faces in the front. So just to give you an idea, just food for thought. So even though that wasn't the purpose of this demonstration, what I'm doing right here, right now, you can figure that based on what your application is trying to do, you could perhaps use certain, I would say this would definitely be something that you'd want to use some math. So you could use certain math to be able to assess distance from the camera. So let's say you had an application that you wanted to be able to pick up people in the back or focus on people in the back versus people in the front. You could probably utilize some math that is able to adjust the maximum facial size. So that'll so playing with that number will allow you to see people that are closer to the camera versus further away from the camera, because the people closer will have larger faces, generally speaking. So think about if this software is actually part of something that you're going to install on a camera, for example. So imagine, you guys can barely even see that. So not that it matters to the discussion, but anyway. So you have some software that you're going to put in a camera like this that you can barely see, but whatever. And you want to be able to coordinate the detection of faces with the focus, right? Focus is something that is distance specific. So you want to set the area of focus in terms of how far away from the lens, closer, further away, right? So to match up the facial detection with the focus, you could tweak that value. So software within the camera could, again, you'd have to use math. So use certain math to correlate the focal length with the actual facial size. So typical size of faces at that focal length, it's other factors as well, but just food for thought. But anyway, so that's it. Pretty simple. Now, the beauty of this, let's actually take a look at one more thing before we wrap up. So we can take a look at the Cascade file. So this is it. This is the magical Cascade file that we're utilizing to be able to detect the faces. And as you can see, this looks very interesting, very fun. But we did not have to really mess with this. This is all the training data that the program uses to be able to detect what a face is versus what's not a face. And you can see it's numbers, numbers and numbers and more numbers and more numbers and more numbers and more numbers, right? Very interesting file, but this is the source file that we used. And additionally, in terms of the math behind it all. So there's certainly a lot of advanced math, but as I demonstrated, you don't need to know the math or be familiar with the math. And you guys can't even see. You guys can't even see the whole time I'm showing you a file and it's not even visible. So I'm sorry about that. Here's the file that we're just looking at. So as you can now see, it's just a bunch of numbers. So this is the actual file, again, with the training data that we utilize to recognize the faces. This is our HAR Cascade file. Now, what I wanted to show you after that was the math behind it all. Not necessarily specifically what we're doing now, but in terms of object detection. So, all right, get your pillows out, and here we go. In the regression-based landmark detection, regression forest is often used to learn the nonlinear mapping from a voxel's local appearance to its 3D displacement towards the target landmark. Inspired by the patch-based methods 10, a voxel is often represented by a local patch centered at it. For better characterization of a local patch, instead of using only intensities, we also extract HAR-like features from local patch to serve as feature representation for each voxel. The HAR-like features are defined as follows. So as you can see, it is as insane as you thought, but as I demonstrated, you don't have to necessarily care, because I think the main requirement is have an understanding of the basic concepts behind it all, but you don't need to know this level, right? You don't need to go to this level. And additionally, I mentioned before, I was talking about downscaling an image and then blurring it out. So some of what I was talking about comes from SIFT, which is, if I remember, it's scale invariant feature transform or tracking. Is it even written here somewhere? Scale invariant. I think that's what it is. Let me see if I can find it. So scale invariant. Oh, it doesn't say it. Okay, but I think that's what it is. If it's not that, it's close, pretty close. So anyway, so SIFT theory and practice. So again, there are strategies that you utilize to detect images. And let's see, where did I want to show you guys? Okay, so here you see scanning of an image and recognizing certain features in that image, but more specifically, and scale invariant. These recruiters are just driving me nuts. So is scale space. 1 second, please. I just love doing live streams. Log finding key points, getting rid of bad key points. Log Gaussian. That is not what I want. Oh, here we go. Well, this is part of it anyway. So this is part of what I was talking about. So this is where they take an image and you blur it and blur it and blur it and blur it. Now, one of the things is before it's blurred, you have all this unnecessary detail. If we're trying to detect the face, we need to focus on just the eyes and the nose and things like that. We don't need to be distracted by all this unnecessary detail. So when you blur it, you're getting it down to the fundamentals. And also you notice that the image is in grayscale as opposed to color. But what I wanted to show you was the scale pyramid, which I thought was right here. Scale space perhaps is the part where it shows that. Here we go. So this is, remember that scale parameter I was talking about before, and I told you about the various iterations. So here you have a series of iterations referred to as octaves. With each iteration, it takes the image and it blurs it progressively. Next iteration, scale it down, blurs it progressively. Next iteration, scales it down, blurs it progressively, and so on and so forth. So it's constantly processing that image at different scales to be able to recognize an actual face in there. Now, scale invariance basically has to do with issues that have to do with scale variations. So I'm processing a video where something is moving closer to the camera. In one frame it's smaller, in the next frame it's larger. How do I consistently be able to recognize what a face is? In the last frame, the face that I found was smaller or bigger, right? So using these methods where in your processing you're varying the scale or scale space, you're able to deal with that. But once again, understand at least the fundamentals, and from that and from a basic understanding of Python, you can utilize the power of machine learning to do facial detection and or object detection. And then you can also look at things like facial recognition. Detection versus recognition, two different concepts. You detect an object by classification. So is it a this? Is it a that? Is it a that? Oh, it is a that. Okay. But that's just an object category. So this is a face, but that's a detection. I have detected a face. Fine. But whose face is it? So again, a lot of different ways to do things, but I would figure the most logical approach for something like that would be to go through several phases. You have a detection phase where you detect a face. Okay, so now we've detected a face. This is now an area of interest. Now what I want to do is I want to identify whose face it is, right? So if you're scanning this image that you're looking at right now and you've eliminated all the background, there's no faces back there, you recognize that this is a face. Okay, so now we're going to hone in on this area and do an analysis of this face versus the data that we have or the database that we have of various faces in terms of names or individuals. So my face, your face, you get the point. Anyway, so can you use Python to find your keys? Technically, yes, but the problem with that is in order to use Python or machine learning to find your keys, you would need to also develop something that allows you to explore the unseen. So you can develop something very easily that can recognize a key, knows what a key looks like. The problem is if your keys are in your drawer, how do you get the data, the image data, to be able to identify it in the drawer, right? You can identify your keys in a photo, but if you have a photo of your keys, then you probably know where your keys are, right? The whole point is you don't know where they are. So you would need to basically process images consisting of the entire space of where you live, right? So in order to get all those images, you need to develop some mechanism for exploration. So we're talking about basically a robot, right? We would need something like a robot, some kind of interface that could actually be able to explore and gain or gather these images. So a robot could actually open your drawer and look at inside the drawer and process the images of what's in the drawer using computer vision, using basically more advanced methods or strategies that I showed you today, and be able to recognize whether there's a key there or not, and then do that around your entire house. So I guess the answer is yes. If you have an Android that is not already capable of recognizing your keys, yes, you could make that Android be able to find your keys by using a program such as this. Add this program to the Android, and now he can use his exploration or search program and couple that with a facial detection program, and he would basically go through the entire house and then run this facial detection over everything that it sees until it finds a key. Now, then we go to the other issue, which is there's detection and there's recognition. So you find something that are keys, but which keys are they? If I'm looking for my car keys versus my house keys, that's another thing. But I think perhaps even just recognizing keys would be helpful, because the robot could say, hey, there's some keys over here, and then bring it to the owner, and the owner could say, no, those are not the keys I'm looking for. But in more precision scenario, the robot would be able to recognize types of keys. So for example, recognize automotive logos. So by recognizing automotive logos, recognize car keys. So if you say, can you find my car keys? It would look in your drawer, see something and detect it as a key, and then run its recognition program to recognize which key it is. And then by looking at the key and turning it over, it would be able to pick up on the logo. So it sees Lamborghini. I have 12 Lamborghinis in my garage, by the way. You'll be able to recognize the Lamborghini logo and then recognize that as an automotive key. And then they can say, well, these are car keys. And then you can bring it to the owner and say, hey, I found these car keys. Now, as far as house keys, I don't know how you'd be able to, unless it already saw what the house keys looks like. I'm not sure I think a basic way, KISS, right? Keep it simple, stupid. So a simple way to approach that would perhaps be an elimination program where it's a most of your keys are probably your house keys and your car keys. I think most people, that's what it's going to be. So keys for your house, keys for your car. So by a process of elimination, if you find keys and they're not car keys, then they must be house keys. If you find keys and they are car keys, well, they're car keys. Well, you know, vice versa, right? If you're looking for house keys and you find some keys and you recognize an automotive logo, then you know that these are not the house keys. So you continue looking. You continue looking until you find keys that do not have automotive logos on them. So that's perhaps a strategy you could utilize to actually find your house keys or find your car keys. So anyway, so there's your answer to your question. Yes, you can use Python to find your keys, but only if you already have an Android. But chances are, if you have an Android, the Android already possesses software where it can recognize your keys anyway. So this would be unnecessary. So there's your complicated answer. If this has been helpful for you, you know what to do. Click on that like button, subscribe for more awesome videos just like this right here on this channel. Salut, wie geht's? Arrivederci.
With options, your entire strategy is based on what you. I'm going to give you the fixed protocol. Options Greeks.
Go ahead and click on that subscribe button and welcome aboard. Also, click on the bell icon. You have to do this.